Somewhere right now, in a quiet control room at NASA's Jet Propulsion Laboratory, a handful of engineers are preparing a command sequence unlike anything they have ever risked before. A single, all-or-nothing reconfiguration of power flows on a spacecraft nearly 16 billion miles away, built with technology from before the personal computer era. One attempt, one narrow window in the coming weeks. If it fails, the fault protection systems could cascade into irreversible shutdowns, silencing humanity's farthest-reaching explorer forever. If it succeeds, it might buy Voyager 1 not just months, but potentially years more of precious data from the interstellar void. They are calling this maneuver the Big Bang, not for cosmic drama, but because it demands an instantaneous, simultaneous explosion of changes across the spacecraft's entire electrical architecture. No gradual tweaks, no second chances, and the clock is ticking down with ruthless urgency. To grasp why this moment feels like NASA's last desperate stand, you must confront the brutal reality of what Voyager 1 has become after nearly 5 decades in the unforgiving expanse. Launched on September 5, 1977, Voyager 1 was never designed for immortality. Its primary mission to Jupiter and Saturn was supposed to end after 4 years. Yet, here it is, in mid-2026, hurtling through interstellar space at about 38,000 miles per hour, having crossed the heliopause in August 2012 to become the first human-made object in the plasma between the stars. It carries instruments that have outlived their creators, powered by decaying plutonium that offers no forgiveness. The 3 radioisotope thermoelectric generators, or RTGs, once produced around 470 watts at launch. Today, that figure has dwindled to roughly 250 watts, dropping by about 4 watts per year due to the 87.7-year half-life of plutonium-238. This is not engineering failure. It is inexorable nuclear physics. Every watt counts in a margin now measured in fractions. 7 of the original 10 science instruments have already been powered down over the years in a meticulously planned sequence to maximize scientific return. Heaters have been sacrificed, systems rerouted around radiation-damaged memory. The spacecraft is a shadow of its former self, yet it persists, transmitting faint whispers of data across distances where a round-trip signal takes nearly 2 days. Then came February 27, 2026. A routine roll maneuver, the kind performed hundreds of times, triggered an unexpected drop in power levels. On a machine this starved for energy, even a small anomaly risks activating the autonomous fault protection system. That system does not negotiate. It shuts down components instantly to prevent overload, with no real-time input possible from Earth. The team moved swiftly. On April 17, 2026, they commanded the shutdown of the low-energy charged particle, LECP experiment, an instrument that had operated almost continuously for 49 years, measuring ions, electrons, and cosmic rays in both the heliosphere and now the interstellar medium. It was a painful but calculated choice to buy breathing room. The LECP's data had been irreplaceable, helping map particle environments alongside plasma and magnetic measurements. Shutting it down was not preference. It was survival. Yet, even in deactivation, engineers left a tiny half-watt motor running, a deliberate placeholder, a thread of hope for potential reactivation if more power could be freed. Because the team had been developing something bolder, something riskier, the Big Bang. Voyager's power distribution was engineered in the early 1970s with generous margins for a 470-watt spacecraft. Decades later, those same pathways harbor inefficiencies that are now lethal. Redundant or suboptimal routing, components drawing power in ways optimized for abundance rather than scarcity. The Big Bang proposes a wholesale, simultaneous swap, turning off certain heaters and devices used to keep thruster fuel lines warm and activating lower-power alternatives in their place. Not sequentially, because intermediate states could trip fault protection catastrophically. Everything at once. A coordinated electrical rebirth attempted through 23-hour one-way radio commands. The stakes could not be higher. Voyager 1 now operates with just two primary science instruments: the plasma wave subsystem, detecting oscillations in interstellar plasma, and the magnetometer, measuring magnetic fields. These are the last direct sensors humanity has in the interstellar medium. Losing them prematurely would create a data blackout lasting decades. No follow-on mission is funded or imminent. Concepts like the interstellar probe exist on paper, but even an aggressive launch today would take 25 years or more to reach the heliopause, leaving a generational gap in our understanding of the space beyond our solar bubble. This is why the Big Bang is not mere maintenance. It is a desperate bid to extend the only real-time lifeline we have to conditions in the vast ocean our solar system navigates. The interstellar medium's density, turbulence, and magnetic properties shape the heliosphere, which in turn shields Earth from galactic cosmic rays. Variations in this shield over time, driven by the Sun's motion through different galactic regions, have likely influenced the radiation environment for life on our planet across eons. Voyager 1's ongoing measurements are not abstract. They inform models of planetary habitability, past and future. To test this high-wire act, the team first turned to Voyager 2, the slightly closer, marginally more power-rich twin. Tests were scheduled for May and June 2026. Voyager 2's trajectory took it past Uranus and Neptune, but its power profile makes it the safer proving ground. If the reconfiguration succeeds there, freeing up watts without triggering autonomous shutdowns, the procedure targets Voyager 1 no earlier than July 2026. As of now, in these critical mid-July days, that window is closing. Engineers have weeks, perhaps less, to finalize, simulate, and execute before further power erosion narrows options to zero. Imagine the tension in those JPL rooms. Commands are uploaded, then silence for nearly 2 days as the signal crawls across 16 billion miles at light speed. Confirmation, if it comes, arrives bearing news of success or the beginning of the end. No live telemetry. No mid-course corrections in real time. The spacecraft must execute flawlessly on 1970s hardware that has already survived cosmic radiation, temperature extremes, and the slow death of its power source. Previous crises have tested them. The 2023 corrupted data stream fixed by rewriting software around a bad memory chip. The 2024 heater command that switched to a 43-year dormant backup transmitter. Each time, ingenuity prevailed. But the Big Bang is orders of magnitude more complex. What makes this attempt feel like the last desperate gasp is the narrowing horizon. Current projections suggest Voyager 1 could continue returning engineering data into the 2030s, but science instruments face earlier limits. Every additional month of operation squeezes more insight from a region no other probe can reach for decades. The persistent plasma hum detected since 2017, a steady, narrow-band oscillation spanning vast distances, remains partially unexplained. LECP data helped correlate particles with these waves. Restarting it via Big Bang power savings could sharpen our models of interstellar plasma physics, distinguishing thermal excitations from quasi-thermal noise mechanisms with profound implications for heliospheric dynamics. Voyager 1 has repeatedly rewritten expectations. The wall of fire at the heliopause with unexpected temperatures. Magnetic field connections between solar and galactic realms. Surprises that emerged precisely because the spacecraft kept going when models said it should not. Each discovery hinged on instruments that were never guaranteed to survive. The Big Bang preserves that possibility, however slim. It is not guaranteed revival for LECP, but it reopens the door by reclaiming efficiency long baked into obsolete design assumptions. Consider the human element. The Voyager team has shrunk over decades. New engineers learned Fortran and assembly to interface with systems their professors studied as history. They debate edge cases in simulations, knowing one miscalculation could end a mission that has outlasted Apollo-era infrastructure. They do this not for glory, but because the data matters. Because Voyager 1 is our lone sentinel, reporting back on the interstellar weather that influences our cosmic neighborhood. Its trajectory will carry it through the Milky Way for hundreds of thousands of years. The golden record a silent greeting, but the science transmissions are the true legacy, fading, yet still defiant. As July 2026 unfolds, the attempt looms. Success on Voyager 2 paves the way. For Voyager 1, the procedure could restore enough margin to sustain the remaining instruments deeper into the 2030s, potentially reactivating LECP for continued particle measurements. Failure might accelerate the inevitable, forcing earlier prioritization of engineering survival over science. Either outcome brings us closer to the day when the signal falls silent, leaving a void no near-term mission can fill. This desperation is born of success. A probe that exceeded every expectation now demands the most creative engineering of its entire life just to limp forward a little longer. The rhythm of mission control in these weeks is one of patient urgency. Commands are crafted with exhaustive verification. Simulations run on modern computers model 49-year-old electronics under interstellar conditions. Teams review every possible interaction between power paths, thermal responses, and fault logic. The communication delay turns every decision into a high-stakes chess game played in slow motion, where the board itself is aging and brittle. Yet they persist because Voyager has taught them resilience. It survived the primary mission, the grand tour extensions, the interstellar transition, and multiple near-death recoveries. The Big Bang is the latest chapter in that saga of ingenuity against entropy. Scientifically, the payoff is immense. Continued plasma wave data refines our picture of the local interstellar cloud. Magnetometer readings track how the galactic magnetic field interacts with our heliosphere. Particle data, if restored, constrains cosmic ray fluxes that bombard Earth over geological time. These measurements feed into broader astrophysics, space weather forecasting for future missions, and even astrobiology questions about protected environments around other stars. Voyager 1 is not just exploring. It is calibrating our understanding of the galaxy's fabric from the inside out. The spacecraft's speed, while impressive, underscores isolation. At 38,000 miles per hour, reaching the nearest star would still take over 70,000 years. It is truly alone, reliant on systems that must function without intervention for days at a time. The Big Bang tests the limits of what can be accomplished at such extremes. It represents the pinnacle of remote spacecraft operations, where human creativity confronts the hard boundaries of physics and time. In the coming weeks, as the command window opens, the world will wait. NASA will update as data returns. Success stories like this remind us of humanity's capacity to nurture fragile connections across impossible distances. Failure would sting, but even then, Voyager's achievements endure as a testament to what careful design and relentless adaptation can accomplish. The probe was built by people who calculated with slide rules. It is sustained today by those fluent in both vintage code and cutting-edge simulation. That continuity across generations is part of the miracle. Voyager 1 will reach one light day from Earth on November 18, 2026, a distance so vast that light itself takes 24 hours to bridge it. By then, we may know the fate of the Big Bang attempt, whether it granted a reprieve or marked the beginning of final descent. Regardless, the spacecraft will continue its silent voyage, carrying data until the last watt fades. Its story challenges us to think beyond immediate horizons, to value long-term exploration even when returns are measured in decades. What Voyager 1 has already given us, firsts in planetary encounters, interstellar entry, and direct sampling of the unknown, outshines any single maneuver. Yet, the Big Bang embodies the spirit that built it. Never accept the obvious limit. Push further. Squeeze one more discovery from the darkness. In these final weeks of preparation, NASA's team is writing the next verse in an epic that began when Carl Sagan and others envisioned a message to the stars. The science it returns is our message back from the frontier. The signal is faint, the distance staggering, the hardware ancient by space standards. But it persists, and in that persistence lies profound inspiration. Voyager 1 shows us that even the most distant endeavors, powered by finite resources and human determination, can illuminate the cosmos in ways we never anticipated. As the Big Bang attempt unfolds, it is not just about saving a spacecraft. It is about refusing to let go of our reach into the infinite until physics itself demands silence. That refusal defines the best of our species, curious, resilient, unwilling to turn away from the unknown even when the odds narrow to a razor's edge. Will the Big Bang succeed in its desperate bid? Will Voyager 1 gain those extra years to keep whispering secrets from interstellar space? The answer lies in the coming days and the flawless execution of a plan forged in necessity. Whatever the outcome, the mission has already rewritten textbooks and expanded our cosmic perspective. It compels us to ask, what legacies will we build today that outlast our lifetimes, reaching farther than we can imagine? Voyager 1 did not just explore space. It redefined the boundaries of what a single, determined machine, tended by dedicated humans, can achieve against the vastness. Its story is our story, one of reaching out, adapting, and listening to the universe's quiet truths. In that light, even the last desperate attempts shine with enduring hope. The signal continues, for now. And in its continuation, we find reason to keep looking up, keep pushing forward, and keep believing in the power of ingenuity to bridge the impossible. Subscribe, stay curious, and witness what happens next in humanity's longest conversation with the stars. The darkness awaits our questions, and Voyager 1 is still answering them.